Structured concurrency is a concurrency paradigm. It's a set of rules. It's a way of organizing concurrent work so that it's easier to reason about, easier to cancel, and easier to handle failures. Let's face it, concurrency is art, and structured concurrency makes it predictable and makes our life a little bit easier. For something to truly support structured concurrency, it must provide three guarantees: bounded lifetime, automatic cancellation propagation, failure propagation. All three rules revolve around the parent-child relationship. So next we'll look at how coroutines actually form that parent-child relationship and create an hierarchy before I explain each rule. This part might feel a little bit abstract at first, but that's completely normal. The good news is you don't need to fully understand all of this to start using coroutines effectively. But once these ideas click, a lot of coroutine behaviors suddenly start making perfect sense. Alright, here goes nothing. Like I said before, threads don't inherently have any parent-child relationship, but coroutines do. But how? We know that you can't start a coroutine without a scope. Every coroutine launched inside a scope becomes a child of that scope. Coroutines themselves can start other coroutines. Because of this, scopes and coroutines naturally form a hierarchy. A scope can contain other coroutines and even other scopes. Here I am just launching multiple coroutines inside run blocking, and I can also create a scope. Coroutine scope gives me a local coroutine scope, and I can launch coroutines inside of it. A scope stay at the top and coroutines branch out from them, and coroutine also branch out from other coroutines. Child coroutines report their lifecycle events and failures back to the scope. This allows the coroutine scope to manage them. I said child coroutines report their lifecycle events, right? How is this possible? To understand this, you need to understand job. When you launch a coroutine, it returns a job instance. A job instance is a handle on the lifecycle of that coroutine. Job tells you about whether the coroutine is completed, cancelled, or failed. A job is a so-called context element, and it is part of coroutine context. We will take a quick detour and explain what a coroutine context is, and then we'll circle back to job again. Bear with me for a minute. What is coroutine context? A coroutine context is a collection of configuration elements that describe how a coroutine runs. And these are the configuration elements. It defines things like where the coroutine executes, how it's cancelled, and how failures are handled. But we are only interested in the job for now. Like I said, job tells us about the coroutine lifecycle. We now know job is inside coroutine context, but where is coroutine context? If you look at the source code of coroutine scope, you can see it holds a property to hold coroutine context. Furthermore, each coroutine you start also contains coroutine context. You can use coroutine context to access whatever coroutine context this runs in. If we access coroutine context in a run blocking block, it gives me the run blocking coroutines context. But if you use the coroutine context inside launch block, it gives me the coroutine context of the coroutine created by the launch. This is the job and this is the thread. When you launch a coroutine inside a scope, the new coroutine inherits the scope's context. The coroutine context of scope becomes the parent context for the new coroutine. During the inheritance process, a new job is created for the child coroutine. That job becomes a child of the parent context's job. All the other context elements, dispatcher name, exception handler, etc. are copied from the parent context unless you explicitly override them when launching the coroutine. Using the same example, you can see the child job coroutine context runs on the same thread, but the job is different. We can also add any other context elements. The parent context doesn't have a coroutine name, but we can give the child coroutine its own name. To do that, just use coroutine name and pass in any name. There we go. We can see that coroutine name becomes a coroutine context. So essentially, the child coroutine inherits the context from the run blocking scope while receiving its own child job. The same inheritance process happens when launching a coroutine inside another coroutine. In that case, the currently running coroutine becomes the parent and its context is used as the parent context. Here's an example. I'm launching a coroutine inside another coroutine that has dispatcher IO. But the parent context, or I should say the scope context, it doesn't run on the dispatcher IO, but it runs on blocking event loop. As you can see, the nested child inherited its parent, which is the launch, which is the child of the scope or the coroutine created by the run blocking. So as you can see, you can sort of nest coroutines inside other coroutines and scopes. The first launch inherits the run blocking context but overrides the dispatcher. The nested launch inherits the context of the coroutine it is launched from. Each coroutine receives its own child job, forming a parent-child relationship. As you can see, the child context has its own dispatcher. It runs on a different dispatcher than its parent. And the nested child inherits the coroutine it runs on. So that's the child context. Inherits its context, but it receives its own child job. Now we know how we end up with a job. Let's talk about job in the next video. If you like the video, please hit the like button and subscribe. And thanks for watching.